Добрый вечер. Спасибо большое, что вы пришли на мой доклад. Я хочу извиниться, что доклад я буду вести по-английски. Просто я еще ребенком уехала из России. Вот, боюсь, что если я буду вести доклад по-русски, то вы мало что поймете, так как терминов я мало знаю. Но вот вообще, если что-то непонятное, у меня большая просьба, если у вас есть вопросы или что-то я объяснила непонятно, пожалуйста, давайте мне вопросы, можно на русском языке, конечно, я постараюсь на них ответить. Okay, so the title of my talk was simplified a little bit, but essentially what I want to talk about is how to detect objects in images. So first, just for those of you who don't know what computer vision is, how many people here have never heard of computer vision? Okay, so most people know this. So I'm going to go through this very quickly. Okay, so the main goal of computer vision is, of course, to enable machines. See if my video will play here. Probably not. But to enable machines to analyze images and detect objects. For example, this Terminator character from the Terminator movie is walking through the scene, and as he walks through, he recognizes there's a motorcycle, there's a car. He'll recognize people that approach him. He'll even determine their size. He's looking for a pair of pants, I believe, to wear. So that's the lofty goal of to enable machines to interpret a scene like this and recognize sort of at the human level of what's in the scene and where. So we're not quite there, but the main approach to computer vision that's been successful is to apply machine learning. So what is machine learning? Machine learning is when instead of programming a computer to do something, we program a computer to learn how to do something, and to learn how to do it from data. So you may have heard this term, big data. This just means that the machine is learning from lots and lots of data. In our case, the data will be image data, images and videos. So where do we find such data? Or rather, where do we find examples of machine learning? So most of you, I'm sure, are familiar with a lot of these existing applications of machine learning, not to images, but to other domains. So for example, machine learning recently, oops, I think it's going on autopilot. All right, let's see if it does it again. So recently, machine learning was able to beat a human at the Jeopardy game and answering questions. Also, machine learning is in a lot of credit card companies use it for fraud prevention. So if you use your credit card in a foreign country, you might get a phone call telling you that your credit card was used maybe fraudulently. So all right, so machine learning is prevalent and fairly successful. And I want to show you this quick clip just to sort of get across the point that even though machine learning has had some success, sometimes it's not, machines are really quite dumb still. So even though in a lot of Hollywood movies you see robots that can do many things, in reality they're actually still quite stupid. And the reason is that machine learning is very, very hard. So here we see a clip from an old movie where there's a robot that is a learning robot, and he's learning how to cook something from a cookbook. So it's the same idea. So the robot is reading a cookbook and following the instructions exactly how they are. And of course, as you see, there's a big problem with that because the instructions are not exactly complete. So he's trying to flip the potatoes, but the instructions didn't say to take the potatoes out of the box. Of course, for a human, this is common sense. But for a machine, a lot of things are not common sense. Okay. So, so we're going to try and attempt to use machine learning to recognize objects and scenes and images. And there's lots of image data out there. For example, personal photo albums. Every time you take a picture when you're out and about with friends and you store it, that's a potential piece of data for machine learning. Of course, there are a lot of websites where you can find such data, YouTube, Flickr, Yandex as well. And there are billions of images out there, and billions new images being created every day on these websites. So really the potential for learning from this data is quite amazing. So what are some common applications of computer vision? Well, so security is one application. We might want to have computer vision running in a video camera that's doing surveillance and catching bad guys. Smart cars is another potential application. I'm going to give up on my videos working today. Scientific images, lots of data about scientific types of problems that we could also analyze. Medical imaging, for example, image-guided surgery. This was work that was done at MIT a while back. 3D images using MRI, CT scan images. These are all images also, so this is all computer vision applications. Vision for robotics, of course, and object detection. So today I'm going to focus mostly on object detection, and this is an example of detecting a specific object, which is a face. So if I were the machine looking at you right now, I would put a little round, a little square red box around each face that I see in the audience. That's the goal of detecting a face. So in fact, face detection is an old problem. As you can see, this is a paper from Computer Vision Conference in 2001, and the method is doing already quite well. But in reality, general object detection is not quite a solved problem. So we're not quite there. It doesn't quite work as well as face detection. So what is the goal of object detection? Well, so if we have an input image like this, for example, and let's say we want to detect the person object or pedestrian is as the case may be here. So the goal is to place a bounding box, or this could be a segmentation mask that gives the outline, the more accurate outline, but mostly people use bounding boxes because they're easier. So we also want to detect pedestrians that are facing away because they're also pedestrians. And in fact, there is a small pedestrian that's occluded in the background, so we'd also want to detect that person as well. So that's the basic task. So why is it so difficult? Well, as you can see here, so this is the result of running a very popular object detector called a deformable part model on an image. As you can see, it's working quite well, but it runs into some problems. For example, here, it's detecting the statue as a face, as a person, where you can't really blame the machine because it doesn't know that a statue that looks like a person is not a real person. It's just like that robot video I showed you. It doesn't have that common sense. Also, there are people that are occluded. For example, it's missing this guy over here because, he's facing away, and you only see a part of him because he's occluded by other people. So in other types of images like this, the task is even more difficult. Here we just have outlines of people against a background. Even though if I asked you, you probably would all do very well and tell me how many people are in this image, but for a machine this is still difficult. Because as we've seen, machines sort of learn from what they have been shown, the examples they've seen. If they've never seen an example of black outlines of people, then they wouldn't quite know what to do here. Another reason why object detection is difficult is it's essentially the sheer number of different objects. So there could be up to 10 or 20 or 30,000 objects that we could be detecting. For example, can you find every object in this image. Probably would take even humans quite some time, especially if I clarify what I mean by object. So if I asked you to put a bounding box around every book that's on the shelf, that's going to be a lot of work. There's lots of books on the shelves, lots of smaller objects, and in general, there's a lot of clutter in this particular video. But this is what the goal is. This is what we're asking a machine to do. Okay, so before I talk about the specific learning algorithm, I want to motivate the approach that I'll describe today. And the motivation is basically to learn from data, we need to not just have images, we also need to tell the machine what's in the image. So we need to annotate. And it's much easier to collect some kinds of data than other kinds of data. So, you know, I just went to Yandex today and I typed in dog, and I got all of these great images of dogs. So it's quite easy to collect this kind of data. Just put a search query into a search engine, and you get pages and pages, sometimes thousands, tens of thousands of pages of objects. But as you can see, this isn't quite enough for detection. So here we actually have not just one dog, but 5 dogs, and we don't know where each dog is. You know, here the dog is down here on the bottom right hand of the image, so it doesn't occupy the entire image. So in fact, sometimes you get images like this that don't even have a dog at all. So they'll just be noise images. Maybe it will be something that just says the word dog or some other source of noise. So even though it's easy to collect this kind of data, it's not exactly useful because to really learn, current methods require that we know where the object, each object is. So we have a bounding box. So just to summarize, it's relatively easy to collect data with these kinds of labels. So if we type in dog into the search engine, we see an image like this, and we say, okay, this is a dog. So this image just has the dog, even though it's not the entire dog, but it's sort of close to being good enough. And the same for this apple here. Whereas these kinds of images are much more difficult and costly to label. So to give you an example, there's a very large image database that has been labeled for roughly 20,000 categories at Stanford and a few other universities. And it's called ImageNet. And excuse me, this data set has, like I said, approximately 20,000 labels for 20,000 categories of this kind. So we just have an image and a tag. Whereas these kinds of labels, which are essential for detection, there are only about 3,000 categories that this has been done for. So it turns out that this is quite difficult to do. You know, it requires a lot of manual annotation. Excuse me. Okay. So the goal of this research that I'm going to talk about is to learn how to learn from this kind of data without needing the additional annotation. So how well can we do that? I'll just show you a little preview of some of the results from our method. So this is not working quite well, but you get the idea. So this is the result of our method detecting pedestrians in cluttered images without any bounding box labels at training time. So we train the method on just generic image search, images like this, and then it's able to, place bounding boxes around the people and do detection at test time. And then this is also the second method I'll describe today, and a preview of detecting roughly exactly 7,000 object categories. So as you can see, it's able to detect this flower pot here. cup or mug here, this whole thing here, the method thinks is a table. I believe this particular detection in the red box is red because it's actually incorrect. It says Boston lettuce, which I'm not actually sure if it is Boston lettuce or not, but at least this is a reasonable mistake. So as you can see, we can actually do something even if we don't have these bounding box labels in our training data. Okay, so the first method that I'll talk about is called confidence rated multiple instance boosting for detection. And this is joint work with Karim Ali, who's a postdoc working with me. Okay, so as I already said, we want to do object detection, and we need a lot of labeled data, but we don't want to have to manually label all of it with bounding boxes, so we want to reduce the requirements for annotation. Now there are several ways of reducing annotation requirements, and these include semi-supervised learning, active learning where the machine asks the user to provide additional labels that are most informative, and multiple instance learning. So I'm going to focus on this multiple instance learning paradigm. So here's an overview of our method. So we start with images like this, which again we just got by typing pedestrian into a search engine. And as you can see, they're cluttered, there are many objects, there are many pedestrians, and we don't have bounding boxes around each pedestrian. And the next stage, we take each image and we generate a set of regions. So we generate a set of regions by applying an existing method for proposing object-like regions in this image. So as you can see, some of these regions do not contain an entire pedestrian, and some of them do, like this one over here. And likely here, from this image, we get some regions that just contain some background, like some trees, and also some regions that happen to contain the actual person. Okay, so now if we knew which of these regions contain the object and which ones did not, then we'd be done. We could then train a machine algorithm from that data, but we do not. So the problem is that now instead of a training image and a label, we have a bag of images, one of which, or at least one of which we can assume is probably the correct object, and a lot of them might be incorrect. Okay, and then so given this kind of data, then we use it as input to an algorithm that we call confidence rated MILBoost, or CR MILBoost for short. And this algorithm learns object detectors from this kind of data. So as I said, multiple instance learning is able to learn from this kind of data where we have bags of examples, at least one of which is positive. Now, traditional multiple instance learning actually is limited in that it can't handle a lot of noise in the bags. So if you have an image like this, and let's say we knew that there was a person here, and then we generated a bunch of regions by sort of taking that bounding box and shifting it around the green bounding box just a little bit. This is a low noise bag. So even though it's not exactly, each region is not exactly on the pedestrian, but a lot of them are sort of very close. So this kind of data is what current multiple instance learning methods are able to handle. However, we have no ground truth bounding box, so we don't have this green bounding, we just have this image. And so, as I already showed you before, we end up with a bag like this. So here we have lots of noise. We have lots of regions that have no pedestrian in them, and some regions that are similar to this, and then we hope to have at least one that has the actual object. So we need to deal with this kind of noise because current methods can't handle it. So that's the motivation. I'll try and go a little bit quicker because I think I'm already halfway through my time. So let's first, just to remind you, or for those of you who don't know, what is multiple instance learning? So in multiple instance learning, each instance has a label. Oh, sorry, in traditional supervised learning, each instance has a label, whereas in multiple instance learning, or MIL, the supervision is weaker. So here our examples come in bags, like the ones I showed you, and each bag has a label. So not each instance has a label, but instead each bag has a label. Then we have two kinds of bags. We have negative bags and positive bags. So a negative bag, we know that all the instances in negative bag are all negative. So if we had an image that contained no pedestrian, we would know that image would produce a negative bag. Whereas a positive bag is a bag that has at least one instance that is positive, but there's no guarantee that the others will be positive. Okay, so just to make things a little bit more formal, in supervised learning, traditional supervised learning, we have training examples x, I, y, I, where x is a feature vector that describes the image, and I'll talk about features in a second, but it's in some d-dimensional space. And yi is the label, which can be -101. Just for convenience, we assume it's a binary problem here, but of course we can extend it to have many different categories. For detection, typically this is a binary problem. We say that the label is -1 if the example is a background example, and +1 if it's an example of the actual object. And then our goal is to learn this hypothesis or classifier, which we do typically by minimizing some loss function L. So this capital L stands for some loss function that I'll talk about later as well. So this is just traditional supervised learning. Again, we have some negative examples and positive examples, and we want to learn this classifier phi that will essentially separate the negative examples from the positive examples. Now, in multiple instance learning, things are different. Instead of a single example, a single label, we have a bag consisting of several examples and a single label. So again, we have positive bags and negative bags. Okay, so the capital Xi is now a bag, and each bag, just for simplicity, let's assume that each bag has k examples, which this is not actually necessary. And then the bags still have labels of -1 or +1, again, -1 for negative bag and +1 for positive. And again, we want to minimize some loss function to learn the classifier, but now our classifier may look something like this, where here the ovals indicate a positive bag, and in fact we might put some of the examples in a positive bag on the negative side of the classifier. So this classifier that I'm showing you, the black line, will actually classify this as a negative example, even though it came from a positive bag. But that's okay, because remember that positive bags aren't guaranteed to have all examples be positive. We know that some of the examples are in fact negative. Okay. Any questions so far? Yes.
Can you clarify that? So bag is just a frame or a picture with several objects with the conditions that if it's positive, there's the single. There's exists at least one, and there is, if negative, there is none.
Right, exactly. So a bag is a set of regions like this, where we know there's at least, so a positive bag is like this, where there's at least one positive example of an object. And there could be a lot of negative as well. And a negative bag is similar, it just does not have any positive examples in it. And we would generate a negative bag from, let's say, images where we look for other objects. So we look for dogs and we assume there's no people. Well, maybe we want to look at pictures of a beach or something. And
The reason behind this to simplify labeling.
yes, to simplify labeling, exactly.
It can be created by just randomly cropping regions from the pictures.
Yes, so we could do random cropping, but in here we use a much stronger method that is an existing method in the literature. Yeah, it's a segmentation-based method. It tries to find segments that look like they could be objects. Any other questions? Okay, so there are quite a few existing MIL methods in the literature that take different approaches to estimate these latent labels. Latent because we don't observe the label of the positive bag instances. We don't know what each label of the instance is. So the simplest approach is perhaps just to take the average of all the input features in the bag, in the positive bag, and create a single feature vector that now we can use traditional supervised learning. So we just take all those image regions and average them and take the average region as our example. There's other methods that, for example, this one will learn a classifier which is sort of the average classifier computed over all the instances in a positive bag, or take the maximum score over all the instances in a bag. In our work, we're going to be basing our work from this method from Viola in '07, which essentially assumes that there's at least one positive instance in a bag. So just to show you what I mean by that, this method is called MIL-boost, and it's using boosting. So boosting is a machine learning algorithm for training a classifier by doing iterations of boosting, where you learn a classifier in a subset of examples, and then you sort of add more and more weak learners to start doing better and better on the rest of the examples. So this iteration is called boosting. So here's an example of how MIL-boost works. So again, we have positive bags. So this, and this are positive bags. And then we have some negative bags as well. Here I'm just showing the negative bags as images. So here each negative bag just has one image. So in MIL-boost, for a specific example in a positive bag, the probability of that example being positive, Pij, where I refers to the bag and j refers to the example or the instance, is given by this equation here. So this is just the sigmoid applied to, so this is a boosting loss function essentially, applied to the classifier score on that example. So this will be close to 1 if we think this example is positive, or it will be close to 0 if we think this example is negative. So it's just the probability. And okay, so in MIL-boost now, to compute the probability for the entire bag being positive, we do this where we say it's 1 minus the probability that all of the examples are negative. So this is essentially saying at least one of the examples should be positive. So this Pi is now the probability that the entire bag is positive. And then, as before, we want to minimize some loss function to get our classifier phi. And in this case, we use the logistic loss. This is a typical loss that's used with boosting. So essentially, we're going to maximize the probability that a positive bag is positive. Okay? Where this probability is defined in this manner. So we might have a classifier that looks like this, or we might end up with a classifier that looks like this as a result of this minimization procedure. So once we have a classifier, then okay, so I should say this classifier, because we're doing boosting, for those of you not familiar, phi, the classifier, is actually a sum of weak classifiers, h. So each hk is a weak decision function. So what do I mean by a weak decision function? So h could just count the number of vertical edges in this image and say, okay, if the number of vertical edges is more than, let's say, 100, then it outputs 1, otherwise it outputs 0. So they're very, very simple decision makers, but by putting together lots of them, so k could be quite large here, by putting together lots of them and averaging their decisions, we could end up with a very strong classifier. So that's the idea behind boosting, which unfortunately I don't have much time to talk about in more detail. Okay, so so what's our method? Because we want to be able to handle noisy bags, we're actually going to do a two-step procedure. In the first step, we're going to estimate the probabilities on the latent label, the way I showed you now. And then the second stage, we're going to integrate this estimate into a new loss. So we essentially want to say, based on the first round of learning, which examples do we think are positive in the positive bag, and which examples do we think are negative? So, and then for the examples that we think are likely to be positive, we want to kind of increase their contribution to learning. We want to say we trust these examples more. But for the examples that we think are not positive or negative, then we want to decrease their contribution. Okay, so just again to illustrate this, we're now going to train a committee of classifiers instead of just one that we had before. With our approach, we're going to have multiple classifiers. And each one will be trained exactly in the same way as before, but there's just now going to be multiple. Okay, so here I'm just showing 3 different classifiers. Each one is initialized randomly, so they will all be a little bit different. Okay, so Q is now a set of classifiers, phi1, phi2, and so on, which we call the committee. And then after we do this, then we essentially compute for each example in each positive bag, we compute how many members of the committee think that's a positive example. Okay? So for this particular image, essentially this classifier, this boundary here, thinks it's a negative example, but these two think it's a positive example. So this will get 2 out of 3 votes if we had only 3 members in the committee. Whereas this example here will get 3 out of 3 votes because all three classifiers think it's a positive example. Does that make sense? Does anyone have questions about that?
So you're practically averaging several classifiers based on their performance.
Right. We're computing. Right. Exactly. Okay. So now we have this variable nu I, which is the maximum over these nu ij's, which will tell us the probability that the whole bag is also positive. So this will allow us to also put a low confidence on an entire bag. So if all the committee members think that all of the examples in the bag are negative, then we'll say, well, maybe it's just a bad image that has no object in it. Because that could also happen with search results. So that's another nice thing that we can do. Okay, so now essentially, in the second step, we're going to retrain our committee, but using a modified loss function. So essentially, the modification is just to incorporate, to add this exponent into our original probability that the bag is positive. So now, if the bag is, like I said, possibly a negative bag, even though it's classified positive, then it's going to have a lower probability because of this additional term. And then we continue iterating these 2 steps as before. And we also end up with slightly modified weights, which I won't go into the details because I don't have much time. So I just want to show you quickly some experimental results. So as you see, it's not a very complicated method, but it turns out to work fairly well. So here the features we're using are very simple, basically edge features. Okay, so I'll show you all at once. They're weak learners. So each of those H functions that I was showing you, weak learners, encodes something very simple about the input image. Okay, so it's just computing a particular orientation of an edge. So here the orientation is this way. Here this weak learner is counting orientations of this direction and so on. And it also has a sub-window where it's computing. So here 2 sub-windows, this is 1 sub-window, and a threshold. Okay, so it's just going to count how many edges of that orientation or that orientation are in the sub-window, and then threshold that count. So it's a very, very simple feature. But because we can have lots of them, we can learn a robust classifier. Okay, so here are some experiments that we did. So the first one is pedestrian detection. We downloaded 200 images from the web and computed 200 regions per image. So these are some example images that we used. As you can see, some of the images, like this one, may not even end up with a region that has an object because the object is very small here. And in fact, that does happen. And then we tested on a dataset called INRIA Person, which has 300 images containing 600 pedestrians. So this is our test data where we know where the pedestrians are and we evaluate the ability of our algorithm to detect them. Here are some example images from that dataset. So the way we evaluate detectors is typically by computing precision. Here precision is on the y-axis. It goes from 0 to 1 versus recall on the x-axis here. So ideally we want to be up here. So we want to have a curve like this, which gives us maximum precision for all levels of recall. And so this is the ideal. As you can see, we don't quite get there. But okay, here, so the black curve here is the performance of a fully supervised classifier. So that's a classifier where we knew the bounding boxes for all of the training examples. Okay, so that's sort of like we did the hard work of labeling just to see how well that would perform. And then the red curve is our method, CR-MIL-boost. Okay, so to summarize, we can compute the average precision just by averaging precision over all levels of recall. And for the fully supervised, it's 52.5%, and for our method, it's 45.1%. So it's not quite as good as having access to all of the bounding box annotations, but it's actually not that far. So the gap here is actually not as far as we would think. It's possibly because you know, the data we used wasn't extremely difficult. Maybe if we used other data, we would have a different result. And then we compared to 3 baseline methods. MIL-boost, which is the one I showed you before, without our confidence committee, and ISR-boost and GM-boost. As you can see, they all perform significantly worse than our method. And the reason they do is again, because they are not able to handle the noise in the bags. Yeah. Yeah, so supervised, fully supervised is the black line.
I see. And where lots of methods.
Oh. So it's basically, it ends up being boosting, just not MIL boosting, just boosting. Yeah, so it's like using MIL boost, but you had an example for each instance in the positive bag, if it's positive or negative. Yeah, it's just add a boost. Yeah. Yeah. Any other questions? Okay, I think I'll skip over this. Yeah, so this is the result I showed you before. It's getting cut off for some reason, but you get the idea. We also did an experiment on horses. Again, downloaded some horse images from the web and tested on INRIA dataset that also has horses in it. And we get similar results here. In fact, we get even higher AP of 57 for CR mill boost than before, potentially because these images might have been easier than the pedestrian images. We do end up having horses sort of just front and center in images more often. But as you can see, this is a very noisy example. We would actually have no horse in this image. We just have the eye of the horse, but that doesn't count. We want the entire object. So this is a negative example for our intents and purposes. Okay. So, and here's some example horse regions that were selected by our methods from bags. So as you can see, some of them are okay, but you know, this one actually it selects multiple horses, but as you can see, it has an entire horse in it just occluded by these other two horses. Okay, so since I'm running out of time, I just want to very quickly talk about the second method I was going to discuss. Actually, how much time do I have? Do I have any time left, or should I stop? Okay. Carry on? Okay. Just stop me when you want me to. Okay. Okay, good. All right, so the second one, the second method I want to talk about is also about detection, without bounding boxes at training time, but using a different approach. So, and this is joint work with my colleagues at UC Berkeley, Judy Hoffman, Eric Zhang, Sergio Guadarrama, and Trevor Darrell. And so again, we come back to this slide that I showed you before, that just to remind you that labels like this are relatively easy to obtain, and in fact, in this ImageNet data set, we have labels like this for something like 20,000 different object categories. But these detection labels are much more costly, so we only have these bounding box labels for maybe 3,000 at most. So what we want to do now is do something different, where we say, okay, let's assume that we have some classification data like this, where we have an image with a tag. And then we also have some data like this, where we have images with bounding boxes for some of the objects. So let's say for apple and dog, we have both kinds of data. We have classifying data and detection data. And then we also have data for other categories where we just have images like this. For example, for cat, we just have images with tags, and we have no bounding boxes for cat. And this is in fact the majority of object categories. Majority of them do not have any detection labels. So what we're going to do, the main idea is to train classifiers on this kind of data, which means classifier just takes an image and just says, what kind of image is it? Is it a dog? Is it a cat? Is it an apple? It doesn't produce a location for the object. And then we also train detectors, which produce a location and a label. And then we try to learn what is the same, what is the common thing about classifiers and detectors. And then we want to somehow take that common thing and transfer it to the classifiers we learn here and turn them into detectors. So essentially we want to now train just classifiers on the classification data and then magically turn them into detectors by transferring this knowledge about, essentially this knowledge would tell us how is classification different from detection. And there are different reasons for why it's not the same. For example, in detection, the image region can be quite small, and the object can be quite small. Whereas in classification, it's usually a larger resolution image. Also, in detection, we want to be able to reject background images. So in addition to classifying into categories, we also want to be able to classify into background, so no category at all. And that's something we can't do with this classification data. So the approach we use here is not boosting, but rather it's a deep convolutional neural network. So these are becoming quite popular these days. And the reason is that they're achieving pretty good results on some of the data sets that we have. How many people know what a deep network is, deep neural network is? Okay, so quite a few people do. How many people know what a neural network is? Okay, so a deep neural network is just a neural network with many hidden layers. So instead of a multi-layer perceptron where you have an input layer, a hidden layer, and then an output layer, you just have many hidden layers, and that's essentially a deep network. This network is also convolutional, which means that the first, well, in this case, 5 layers, generally the first several layers, the neurons in those layers only see a small location in the input image. So they're not applied to the entire input. They're only applied to spatial mask in the input. And also the parameters of those nodes are shared across all locations. So, okay, so here what we're going to do is we have our classification data. So for cat, we only have classification data, no detection data. And then we also have some classification data for dog. So we're just going to train a classification network. Okay, so this is the output layer. And these two are 2 layers that follow the convolutional layers that are just fully connected layers. So they're just learning some nonlinear function. And then the output layer is just saying, you know, the first neuron in the output layer would give us a value of 1 if the image had an airplane, or if the image had a cat, this neuron over here would give us a very high value. So here we're getting 0.9 because we had a cat as an input image. So this is just classification. Okay, we put an image in, and it tells us what category that image is. So this is the network up here. And then the next thing we do is we adapt this network for detection. So we have some additional data that has detection labels, that has bounding boxes around objects. So we start with the parameters of this network, and we fine-tune, or we continue learning using backpropagation, just the typical learning method for these deep networks. But just starting with the parameters of this original classification network. And so the only difference is now our output layer is different. So we no longer have any output layer for cat and airplane because we have no detection data. We have no data to train this network with for those categories. But we still have an output layer for dog and other categories that we do have detection data for. And notice that we have this additional node in this is just a single node neuron in the output layer that fires when the input region is background. So it's none of the categories, it's just background. Excuse me. Any questions on this? I know I'm going pretty fast.
So background classification should be computed separately. With, if you already have pre-trained previous layers, but you pretty much have to get your data and just cut out all the recognized images and try to see for the output?
No, so because we have these bounding box labels, the input to this network will be the regions, just like I showed you the bags, we have these regions. So it won't be, yes, sorry, I forgot to mention that. So we're not going to be using whole images, we're going to be using regions. And for the regions that have the actual object in them, the label will be one of the categories. But for a region that has background in it, then the label will be background. Okay. Yeah, so that's, and the red here is just to indicate that we're going to learn this from scratch. We didn't have this in this network at all because we didn't have any background. The whole image was assumed to be the object itself.
Is it the same algorithm for creating regions? The same as in the previous part?
The learning algorithm?
No, I mean regioning for...
Oh, the region proposal. Yeah, it's the same one. It's called selective search. And it's a recent method.
So output proposals are generated by fully connected A and fully connected B. I just don't understand the difference.
So the difference between these two is the data is different. So here the input images are images like this where each image contains one object. And the output is also different because we only have as many output nodes as we have categories. So dog, cat, and so on. This is quite simple. Well, I mean, classification and detection tasks are actually not that different, right? That's why maybe you're not seeing the difference. The only difference here is the input data is regions produced from the original image. So it's a region like this, which just has the dog, for example. Or it's a region like this, which has no object at all. Okay, so and if it's a region like this that has the dog, then the output layer is set to say dog. The output of the first network is n, it's n values between 0 and 1, where n is the number of categories. And the output of the second neural network is n plus 1 values between 0 and 1, where there are n categories. Well, yeah, for each region. For each region, yeah. Yeah, so for each region, we apply this neural network, and it tells us if it's one of the categories or background. Yeah.
How do you produce regions from the source?
So we use an existing method called selective search, and essentially looks at, it just tries different bounding boxes, and it picks bounding boxes that look more object-like. For example, if a bounding box contains some blob or segment that doesn't overlap, it's the bounding box. So like this dog is mostly black. So there's some segment, some black segment that does not overlap that bounding box, and that bounding box will be promoted. Yeah, so I just didn't have time to talk about that method here. It's not our method, it's something that we use off the shelf. Okay. So, all right, so the only difference is that we're fine-tuning and changing all of these neurons, the values of all of these neurons, and plus we're learning a new background output node. Okay, so now the last step is very simple. We just take this output layer from the classification network, just the way it is, and we plug it in here to this network. Remember, we didn't have this output layer. We couldn't fine-tune this on the detection data because we had no detection data for these object categories. Okay, so imagine these are the 20,000 object categories that we have no detection data for. So here we just take that output layer and plug it directly into this network. Now, this may not exactly work because remember this layer, for example, the output of this layer has changed because we've fine-tuned, we've continued training it. So the outputs of those neurons have changed. And so before this FC7 layer was producing slightly different or maybe very different outputs. And that's what this output layer was trained with. But now this could be different. So that's why we're doing a little bit of kind of transformation on this output layer, just to make it accept the new fine-tuned FC7 layer outputs. And then we're done. So now we just have a detection network that can detect all of our categories, not just, yeah. So yeah, so the adaptation is very simple. We just take, for each node in the output, we find k-nearest neighbors. We take the weights of each node, and we find the k-nearest neighbor weights in the detection network. And we just learn some it's just a regression function, essentially. It's a regression function between how the weights change from here to here.
So green classifiers are the training examples, and blue classifiers are those which you address the linear transform, or so what are you regressing? What are you predicting?
So we're predicting, yeah, essentially how the weights of this green classifiers changed from here to here.
It's a linear transform.
I believe it's a linear transform, but you could use any regression, really. Yeah.
It's not a vector, it's a matrix.
Right. Right. Yeah. Okay, so just quickly show you some results of this method. So these are results on the ImageNet Large-Scale Visual Recognition Challenge dataset. And there's two types. There's classification and detection, and we're evaluating on detection part. These are other methods that were evaluated on this dataset. RCNN is the current top performing algorithm. This was just shown at CVPR a few weeks ago. And it's doing something very, very similar. In fact, one of the authors is on this paper too. It's doing something very similar, but not this adaptation and this transfer from classification to detection. So in fact, RCNN needs bounding boxes for all of the training data. And then our method is here, this orange line. So as you can see, okay, and now I should say that here we're training on only 100 of the 200 categories, where we have bounding boxes for only 100 of the 200 categories, whereas RCNN has bounding boxes for all 200. So it's that same setup where if we pretend we had bounding boxes for everything, we get this performance from RCNN. If we throw away half the bounding boxes, we get this performance. So it's not as high, but it's actually higher than some other methods, some other recent methods that use all of the bounding boxes for training. So this, let's see, this is the performance on all of, okay, so this is evaluated on the 100 that we didn't have detection data for, and this is evaluated on everything, on all 200. So the point is that we're getting competitive performance. I'll skip this part and this part. I'll just show you some nice results. So here, some example test images, and I'm showing in red the bounding boxes that we get if we just run the classification network on the regions. So we take the image, we produce lots of regions, and on each region we run the classification network, and we take the highest response. So if you run the classification network here, the red bounding box is the result that had the highest response for this category of whale, and as you can see, it doesn't localize the object very well, whereas green is our network, our adapted network for detection, and it localizes the object much better. Here's another example. Red is the classification localization, and green is our localization for motorcycle. This is again, we're showing improved localization for boat. So in all of these images, both networks predicted the right object. But our network was much better at localizing the object. Here again, the classification network just fired on the face of the lion, whereas our network, detection network. So, and the important thing to realize here is that these detectors were not trained with any ground truth bounding boxes for these categories. So we didn't have any lions with bounding boxes. We didn't have any lemons with bounding boxes. Yeah.
So what was the closest category to a lion that you had in your green set?
So to tell you the truth, we took the first 100 for training and the next 100 for testing. So it's a very good question, but I don't have an answer. It's possible we had. I mean, there are a lot of animals in the, but for example, this is a washing machine. I doubt we had anything that close to a washing machine. So, okay, so here's some examples where our detector predicts the correct bounding box, but incorrect object. So it said this was a microphone, this was a mini skirt, this was a motorcycle, where in fact it's a bicycle, and it said this was a mushroom, where in fact it's some kind of moth. Here's some more. It said this was a nail, this was a laptop, and this was a lemon. So, I mean, these are fairly intuitive mistakes that even humans, I think, might make. Okay, and here's just the very last slide I'll show. These are some very preliminary results on extending this beyond the 200 categories to 7,000 categories. So here we have an input image where we can now detect 7,000 categories, and it says this was a wall clock, sliding door, TV or monitor here, so that's wrong. Abacus here, tray here, and flower pot here. So as you can tell, it's not always telling us the right object, but it's getting some of them. And again, we weren't training with any detection data for those objects. Here, this is whippet, which I think is a type of dog, but not the right type. This is a dog. This whole thing is a sofa. I showed you this one already. Bison, helmet. This one, it said person. Not sure why it's incorrect. Bicycle, mobile home, manufactured home, it said for this wall. This is a house. Convertible for this. Car mirror and car wheel. It missed this wheel, obviously. This is a very cluttered scene. Analog clock, carton, chair, chair, table, chair, table, chair. So, I mean, obviously, it doesn't have training data for the exact kinds of objects that we see here, so sometimes it just will get the closest object that it has in its training data. Stethoscope and person. Okay, I'll just end here. If there are any questions, oh, I'm done. If there are any questions, please ask.
Hello. So I wanted to ask if where is this paper going to be published? The last one that you showed, adapting convolutional networks for detection.
So that paper was submitted, so it's in review. But we'll publish an archive tech report.
Okay.
And the first paper was published at CVPR this past month.
So what kind of archive?
Just archive ARXIV.
I got it. Ah,
Yeah.
you mean arXiv.
As a tech report, just a tech report.
Okay, and the question is, it wasn't clear. The second adapted network was outputting the the coordinates of the bounding box, or was it just okay?
Well, so it wasn't. It was not outputting the coordinates of the bounding box, but remember the input to the network is already a bounding
Yeah,
box.
patch.
Yeah,
Some
it's a
patch.
patch.
Mhm.
Yeah, so it just says if it's one of the classes or background.
Okay, thank you.
Thank you very much for such very interesting lecture. And my question is, are there any available maybe program realization, maybe APIs of MI learning algorithm?
Yes, there are available APIs for MIL. So there's latent SVM, which is essentially the same thing. I don't know if you've heard of latent SVM. It's a latent variable SVM, but it essentially does the same thing as MIL. That's for SVMs, and MIL boost is the version for boosting, for ADA boost. And then if you are interested, you can email me or my postdoc Karim Ali about our version of the CR MIL boost.
Okay, I mean, so for example, I can see some code, maybe examples or something like that.
Yeah, exactly.
Okay,
yeah.
Thank you very much.
Sure. And I should also say that the neural network stuff is implemented using Caffe, which, yeah, I don't have a citation here, but if you just search for Caffe, C-A-F-F-E, or Caffe UC Berkeley, those guys have this really great implementation of deep nets. You can train it on GPUs or on CPU, either way. Sorry, I forgot to plug.
The question is, how much regions were selected for analyzing for each image? I mean, I guess there are lots of overlapped regions, and these regions should be tested. And how proper classified regions were selected? Because if there are two overlapped lemons, and we have different combinations of overlapped regions that includes one lemon, for example, or two, how these problems were solved? Thank you.
Yeah, so that's a very good question. So in the case of overlapping lemons, so here, for example, you see how the classification network is saying this whole image is a lemon. And that's because that's what it was trained on. It was trained on images like this that might have had multiple lemons in it, but the label was it's a lemon. So it has no concept of multiple lemons or multiple objects could be there. So the classification network makes that mistake, but our detection network was actually trained on well, it wasn't trained on lemons, but it was trained on other objects where it knows, okay, if I want to find just one object, so it knows not to do that.
Here is the region with the best probability of lemon from a whole picture, right?
Yeah, that's right. The highest probability. Yeah, and there's also a step of, to answer your question of how many regions we initially create, I think it's something like 2,000, but it's really limited by your CPU time. It's how long you have. Any other questions?
Thank you very much. A little bit of philosophy. You showed a slide where you have lines of probability your method works. And as I understood, supervised learning gives you not very good results comparing to the ideal methods.
Right.
Do you think this way of building labeling systems is maybe a dead way for studying? Maybe you should combine this method with maybe stereo methods, or maybe some other sources of data to combine with images to make these methods more confident, more probable. Because this line, you showed that the supervised method is not ideal, but your methods use this line as a asymptotic line.
Right.
Thank you.
Yep. No, that's a great question. Yeah, so I was showing you face detection before. And for face detection, that supervised line would be pretty much ideal. But there are very few categories for which we can achieve that right now. And one of the bottlenecks is training data. So that's why I'm trying to solve this problem that we just don't have enough training data. If we could add stereo, I'm sure that would help. But we just don't have the training data with stereo in it. You know, we have this image net with 20,000 categories, and that's what people train with now, because that's the biggest amount of labeled training data. Of course, there's lots of just images online, but they're not labeled, so they're not as useful. As far as what if I think it's a good approach, I don't think that's the right approach just by itself. I think ideally we would be using depth if we had access to it. For example, if we had a robot that actually could have a Kinect on it or something that would have depth input, I think that we should use that. If we only have a single image, I think here it's a very good example that we need to use context of the whole image. So we know, for example, that a wall clock is likely to be on the wall. That's fine. But maybe a crate shouldn't. So it said this whole thing here is a crate. There shouldn't be a crate or a box floating sort of at the top, right? So we should be using some context to use that knowledge of where things should actually go in a scene. And not right now, the algorithm is just showing at that single region is just trying to guess what that is. It has no idea of what else is happening in the image.
And the other question was about, do you know about some studies that use your labeling? You said that you have 20,000 labels, and the semantic network will be very great for this. You know, if you have this semantic network, you can say that if you have a C and you have a dog, that they maybe should not be in the same picture. Do you have any information about such studies?
Yeah, I think there are some such studies, and in fact, I have a recent paper on recognizing activities from YouTube videos where we used semantics that we extracted from text data about what subjects can do what actions to what objects. So, for example, if we have a person can walk the dog, but a person cannot ride the dog or is less likely to ride the dog. So if our visual detector is saying that it's a person riding the dog, this semantics knowledge we learned from text will downgrade that decision, essentially. So that's just my own work, but there are other studies as well that do that kind of thing.
Thank you.
Okay, so let's just thank the speaker for a great talk.